Good evening. I'm Richard S. McGee, and you're watching The Learning Tree. Sitting to my right is Dr. Joel Rubin, who is a professor and a teacher. He is a teacher at Stoughton High School, a professor at Cambridge College, and at Boston University. And he's going to excite us, enlighten us, and carry us through the earth into the sky and there beyond. Talk to me, Dr. Rubin.
Well, thank you for inviting me to come in tonight.
You're quite welcome.
I have been teaching astronomy at Stoughton High School for the past 8 years.
Now let's talk about you. Who are you? How did you come here to be who you are? What is a little bit about your background, your person?
Well, I have been a student of many subjects over many, many years. I got out of high school and went to art school.
Where did you go to high school?
I went to Newton South High School.
Okay.
And I prepared myself to be an artist, and I went to the Massachusetts College of Art, where I got my bachelor's degree in fine arts and my master's in art education. Just in time to find there were no jobs for art teachers because of a new law, Prop 2.5, which cut the budgets.
All right.
So I trod around on the edges of education for many years. I worked at the Museum of Fine Arts. I worked at UMass Boston. I got a master's degree from them in critical and creative thinking, and I ran science festivals and art festivals.
So you have 2 master's degrees.
I do.
All right, continue.
And I went to work for the New England Aquarium in 1990, and I worked there for 16 years, running their teacher services. And in the process, I also got myself into the ed school at Harvard and worked towards my doctorate, which I earned in 2006.
All right. And you graduated.
I did.
And here you are sitting in front of me. All right. Tell me now, you and I are going to discuss astronomy and astrology. So let's start out with some definitions. First, define astronomy for the people who are interested in the subject. And then, after you've completed that, define astrology.
All right, I'll try. Astronomy is perhaps a more recent name. Astrology is perhaps an older name. They both come from astra, which refers to the stars. And it's the study of the stars, the laws of the stars. But really, it's a study that looks at everything that takes us outside of Earth.
That's astronomy. Okay. And how about astrology?
Well, astrology was the long-standing belief that the stars cared about us.
That they did what?
That they cared about us, and that whether we woke up in the morning or stayed in bed with the covers pulled up over our eyes would depend in some measure on what star was where in the sky. In other words, a species of fortune telling.
Okay. And when did astronomy begin? The concept, the idea?
There are pictures painted on the caves that seem to indicate.
On what caves?
The caves that were inhabited by painters 25, 30,000 years ago.
Yeah, in what area?
In France and Spain.
Okay.
But they've also found work in the American West, where people set out stones as calendars, they think, and in England, where they set up stone monuments like Stonehenge. And they probably made things out of more perishable materials, but those haven't survived to this day. But the stones are still where they were placed, and so we think that they had knowledge of the passage of the seasons and the turning cycles.
What era are we talking about?
We're talking about tens of thousands of years ago.
Give me a figure. When you say tens of thousands, what? 1600s, 1400s,
Well, it's
1300s?
I think it's somewhat indeterminate.
Oh, okay.
You know, because there have been successive occupations of places over very, very long periods of time. I mean, I was just reading in the newspaper last week that they seem to find evidence of our species in West Africa 250,000 years ago, now they're saying. You know, and when I was first being educated about those things, they were saying 100,000 years ago. You know, so we're talking about very large amounts of time, and the ability to measure within those times is it's a difficult thing, and it's contentious. People debate about that. But you know, if you could roughly say that civilization has been going on for about 10,000 years, what we think of as settled communities now, it matches to a great extent the period of time that sea levels have been stable since the last ice age. And so people could set up communities on the coastlines and pretty much count on the ocean staying where it was, and their city being a port where they could send ships across the sea. And when they were out of sight of land, they would use the stars to make their maps. And that was true in the Mediterranean Sea. It was true in the Pacific Ocean. And so around the world, people have charted the stars and used them as guideposts in their travels.
Were the Chinese very, very active in creating some of these maps?
There are maps from...
What countries were?
Well, China, let's talk about that
Yeah.
momentarily.
Yeah.
The Chinese recorded 1,000 years ago the explosion of a star that magically appeared and stayed in the sky for a period of time and then disappeared from sight again. But at one point, it was so bright that they could see it during the daytime. And they reported about this, and their map, which shows its location, allows us to pinpoint where that star exploded at that time, over 1,000 years ago, so that today, with telescopes, we have the ability to zoom in on that part of the sky and see the cloud of dust, the nebula left over from that explosion over 1,000 years ago. We call it the Crab Nebula.
What other countries were active in mapping?
In mapping the skies?
Right.
Well, I don't know if you can call them countries or nations, but the people of the Pacific
How about
Island,
India?
the people of the Pacific Islands,
Yeah.
they created star charts that they used to navigate across the largest ocean on our planet.
And how about the Middle East?
The Arabs are famous for having maintained and developed astronomy to a high level. In India, they have beautiful observatories that were constructed to map the stars. So it's a worldwide study that has taken place. But you know, in our society here, we mostly go from a tradition that started with the Babylonians and that was passed from them to the Greeks, and from the Greeks perhaps to the Arabs, and then back into Europe after that.
So these were very active mappers in this whole process.
Yes, so I think there were a couple of reasons behind this desire to chart the sky. First of all, you have people without TVs or internet or electronics. They're out there looking up, and they're putting together stories to explain their cultures. And these stories could be guided by the stars, by seeing patterns in the different stars, and using those to connect the dots, if you will, for the traditions that they upheld. And then you have the aspect of navigation, of seeking to find your way. You have the aspect of agriculture, where the changing patterns of the stars with the seasons were associated with the migrations of animals and the times to sow crops, and when you could expect to find this and when you could expect to find that. So they allowed you to make life more predictable. And then above that, you have the wealthy people who would hire astrologers to tell their fortunes so that they could predict what they should do on this occasion or that occasion.
Let's talk a little bit about astronomy. What are you've got some active material here. Which one of these would you like to begin with to explain what you've got here behind me?
Well, both of these objects were made by a couple of my students a few years ago, Shaquan Larkins-Gooding and Fabrice Emile. And when they were my students in the astronomy course, I asked them if they would help me to create a model of a galaxy and a model of the graph that is used to describe all of the different kinds of stars that there are. So this is a model representing the temperature and brightness of all the different kinds of stars that are seen. And this is a model that represents the huge collection of hundreds of billions of stars in a single structure that orbits a central supermassive black hole. And in an object such as this, a galaxy, I've had them glue a ping pong ball to represent one of these exploding stars, like the one the Chinese described 1,000 years ago. And these exploding stars, these supernovae, are as bright as the light of the entire galaxy. So a single exploding star of this kind can be equal in brightness to hundreds of billions of stars, an entire galaxy. And so it acts as a kind of lighthouse from across the universe that astronomers can use to measure the distance to these objects.
So let's go through this one. Let's do some stepping through here.
So this is commonly called an HR diagram after Hartsprung and Russell, a Dane and an American, who both invented it the same time, early in the 20th century. And it's a way of understanding the life cycle and activity of stars in terms of their brightness going up the scale and their temperature going across. The center is a yellow star like our sun.
These two here.
Yeah.
Okay.
And the sun is our unit of comparison for all other kinds of stars. We think of the sun in astronomy as being an average kind of star, not one of the great enormous stars and not one of the tiny small ones, but more or less in the middle in terms of its mass, its probable lifespan of about 10 billion years, which we're about halfway through at this time, and about middling in its mass, its brightness, its temperature, its lifespan. And it has an interesting relationship with other kinds of stars, because you can see there's a diagonal line rising from the smallest and dimmest.
Now, those are the dimmer.
The lower right-hand side are the red dwarfs. These are the smallest stars, and the ones that have the longest lives and the lowest temperatures. They're only about as hot as your toaster oven. And then you go all the way up to these blue giants in the upper left-hand corner, which glow primarily in the ultraviolet range, like the heat of welding, arc welding that melts metal. That's the kind of heat that
now,
they
are
have.
these defined in terms of distance from the Earth?
Distance can be estimated based on this vertical axis, which represents the energy output. The brightness can be thought of as the amount of energy that this object is emitting. And so we have stars that are fairly dim in the lower right-hand corner and in the lower left-hand corner, but for different reasons. And we have stars that are bright in the upper part, and the brightness of the star can be compared to how bright it seems to be from here, where we're looking at them from. Because a star can seem bright to us because it's really bright, or it can simply seem bright to us because it's close. And a star that is naturally very bright can seem quite dim to us simply because it's very far away. So there's a difficult puzzle to be worked out. Is a star bright because it really is, or because it's close to us? And is a star dim because it really doesn't have a lot of energy, or because it's really far away?
How do we make that distinction?
There's a mathematical relationship between the true energy output and how bright it seems to us from here.
Okay.
It follows what's called an inverse square law. So that if something is 3 times further away, it's 9 times dimmer. If it's 10 times further away, it's 100 times dimmer, and so forth. And so mathematically you can say, okay, we measure how bright it seems to be. We know what its true energy output is because of the kind of star that it is. And when we compare those two numbers, we can work out its distance.
And that tells you what the distance would be.
You can use the true energy output, if you have a way of detecting that, compared to its seeming appearance, and the relationship of that is the inverse square law, such that if it's 10 times closer, it's 100 times brighter. If it's 3 times closer, it'll be 9 times brighter. And because of that mathematical relationship, you can estimate the distance. But the problem is, how do you know what its true energy output is?
And the problem I'm having is the star that's very bright, but very far away, but appears to be dim. How do we know that to be a fact, that it's bright? If it's so far away that it appears to our vision that it's not very bright, how do we know that the factual statement here to that extent?
So,
is there some way to measure
yes.
that so that you can? Is there some way to determine what that real vibrant light would be if it were closer?
Yes. It depends on what we call a standard candle. If you bought a box of candles at the store, and every candle in the box was exactly the same, and you set them up 1, 2, 3, 4, you could measure how they gradually came to seem dimmer the further away they were, but you know they all came from the same box and have the same intrinsic brightness. So you're looking for stars that are like that you can consider to be standard candles of the same kind. And the first were discovered.
So there's really an assumption made that if you find like kind of stars, and they're bright up front when they're closer, and they're now a distance where you assume that they also are still as bright as the star that's confronting you, in front of you.
So
is that an assumption or a fact?
Like all science,
okay,
it depended on close observation of a very, very large sample of stars. In the 19th century, Harvard had an astronomer named Pickering who hired a group of women to analyze millions of stars on thousands and thousands of glass photographic plates. And these stars had been photographed using a prism that would
Okay.
break their light into rainbows.
Okay.
And these astronomers at Harvard, women like Henrietta Swan Leavitt
Mm-hmm.
and many other important people who looked at these stars throughout their lifetimes, broke down the different categories by their spectra. So they found that in a laboratory, you would understand that when you saw this type of spectra, you were looking at something that was composed of hydrogen. And if you saw this kind of arrangement of the colors, you would know that you were looking at helium. And so they determined what the breakdown of all the different kinds of stars were by their composition, and they figured out that there were certain types of stars that got brighter and dimmer, that varied like clockwork, and that you could tell the true energy level was directly related to the period of their brightening and dimming. You could measure this type of star, examples of this type of star, by geometry. They were some examples that were close enough that you could form a type of triangle and perform trigonometry to measure the distance to these stars. And so they calibrated this method, which was discovered by Henrietta Swan Leavitt.
Okay.
You could calibrate the relationship between how many days or hours it took for the star to go from its brightest to its dimmest with the true energy output of that star as measured from geometry. And then you could extrapolate to, if you saw that type of star in a galaxy, you could measure the distance based on that direct relationship between how many days it took for it to go from bright to dim and what the true energy output of a star of that power would be, and compare that to what it looked like from here on Earth. And you could see that relationship using the inverse square law. Well, if it's 10 times further away, then it must be 100 times dimmer. So if it looks this dim, then it must be, 10 times further away.
Is that true of these smaller bodies?
So they found stars of every single type, all the different types, from the red dwarfs to the blue giants, the white dwarfs, the red giants, all of the different kinds of stars. They found examples that were close enough to be measured geometrically. And once they had analyzed these based on their spectra to recognize what were the materials of which the different kinds of stars were made, then they could extrapolate and say, if we see this kind of spectra for a star, then we know it's a red giant. Whereas if we see a different kind of spectra, then we know that it's a red dwarf.
Okay, now these moons over here,
Not moons.
stars, are what is their relationship to the rest of this?
So stars are typically born in nebulae, which are large clouds made up of materials left over from previous generations of stars going back in time.
Okay.
And eventually something may happen that causes the cloud to condense. Perhaps an exploding star shocks the system and causes things to get close enough.
Supposedly that's the theory of how the Earth was formed, right?
The solar system.
The Earth was formed
As,
from an exploding star.
so as one of the effects.
But I didn't want to go there yet. You're going to tell me about these stars over on the right here.
So the stars at the top
Now,
are thought to have the strongest gravitational
the blue.
force. Yes, the blue
Okay.
giants, the strongest gravitational force. And this causes them to have incredible heat and pressure because of this gravity that's pulling inward on their material. And so they burn through their huge mass of hydrogen more quickly than other kinds of stars. Stars that are smaller in mass are thought to have weaker gravitational force, and so they don't burn as hot. So the stars that are most massive and that burn hottest are thought to burn through their fuel within a few million years, while the stars like our sun in the middle are thought to last for 10 billion years. And the stars that are down in the lower right-hand corner that have the least mass of all burn so slowly that they are thought to last longer than our universe has been measured to last for. So
Okay.
you could say they're too cool to die.
Okay.
Stars like these red giants,
Okay.
which are similar in temperature to these red dwarfs, are thought to be a stage later in the life of a star like our sun. When our sun has burned through most of its hydrogen, its core will contract, and the outer layers won't be held as strongly by the gravity. And so the atmosphere of the star will begin to puff up into a large, loose structure, which we call this red giant. And eventually, those outer layers will evaporate and reveal what had been the core of the star, which we call the white dwarf.
And that down at the bottom there?
Yes.
Those are the white. Okay.
So it's a story that goes
Is it-
from,
Are you saying that these used to be much larger?
I'm saying that the white dwarfs are the cores left
core,
over
okay.
from stars like our sun.
All right.
Stars like these blue giants in the upper part are so massive that when they run out of their fuel, they will explode in what's called a type 2 supernova. And the results of that might be a neutron star or even a black hole.
Okay. What about the holes?
The black holes are objects of such great density, the cores of supermassive stars, that their gravitational well is so deep that not even light can emerge from it.
What kind of depth do they have?
If you were to replace our sun with a black hole of equal mass, we would notice no difference in the gravitational effects at our distance,
Why is that?
because our position in the solar system is based on the mass of the sun, mostly, and our mass as well, the mass of Earth. So if an object of equal mass, whatever it was, were to take the place of our sun, not that this could happen,
And the black hole is a very huge mass.
right? But
Definitively.
I'm just extrapolating.
Yeah,
if you
okay.
took a black hole,
Yeah.
if there could be a black hole that was no bigger than our sun, which I don't think is possible, but if our sun was replaced with that, we would lose the light and the heat, but the gravitational effect would be no different than an object of any other mass equal to the sun, which sort of brings us to the measuring unit
Okay.
that we use in astronomy, which is to compare things to our sun. So
Right.
we compare the brightness of stars to our sun. We compare the temperature of other stars to our sun. We compare the lifespans of stars to our sun. And we measure the masses of objects throughout the universe based on the mass of our sun.
Does the sun have the same impact on all bodies in space as it does on the Earth? Or is it a central kind of thing? the certain bodies are affected by the sun?
The formation of a planetary system, like our solar system, is a long process that starts with clouds of dust and gas. They condense. They begin to go around each other through self-gravity, like wrestlers circling each other in a ring. Gradually, things that aren't going in the same direction collide and get absorbed until one plane of motion begins to dominate, and gravity brings material in towards the center, and gravity works most strongly above and below the plane of rotation, while at right angles to the axis, inertia tends to keep things where they are. And so gradually things thin out, sort of like when you toss a pizza up in the air and you develop a structure called an accretion disk, a disk of material that orbits around this central mass. As material continues streaming in from above and below, this central mass increases its gravitational force, its heat, and its pressure until so much has accumulated there that the strong atomic force is overcome and nuclear fusion begins, and the star is born. Our sun was born like this. And what's happening is hydrogen, the single proton, the simplest element, now comes together with other hydrogen atoms, and two of them make a single helium, and the single helium weighs a little bit less than the two hydrogen from which it was made, because some of that mass was converted to energy. And so many of these atoms are being converted from hydrogen to helium at such a rate in an object as massive as a star that we have this incredible ball of incandescent, fiery matter.
Okay, tell me about the Milky Way.
Our galaxy.
What?
Our galaxy.
Our galaxy. Our galaxy. Why is it called the Milky Way?
Long ago, when people looked up at the sky at night, they would see this line running across the sky. And they would associate it with some of the star patterns, like the swan and the eagle and the centaur, Sagittarius. It was only after Galileo took a telescope and looked closely at it, more closely than had ever been seen before, that he realized it wasn't just a stripe across the sky. It was composed of uncountable numbers of faint stars. And over time, people developed the ability to determine the distance of these different parts of the sky, at first by geometry, later by these standard candles. And they began to map out the shape and begin to realize that we were inside of an enormous disk consisting of hundreds of billions of stars. And there was a great debate whether this was the entire universe or whether there were other such structures in the universe. And this debate was settled in 1923 when Edwin Hubble directed his telescope at what we now call the Andromeda galaxy. What was then thought of as another cloud of dust and gas in the universe. And he saw a standard candle a Cepheid variable of the type that Henrietta Swan-Leavitt had described, and was able to use the rate at which it pulsed to determine that it was at such a great distance that it could not possibly be part of the Milky Way, and that that structure, what we now call the Andromeda Galaxy, was like our own galaxy, a structure that itself consisted of hundreds of billions of stars.
Let's talk a little bit about the telescope. When did it come into existence, and under what circumstance? It became the major instrument for measuring, for looking at least at stars. Can you remember what year that that came into existence?
Early in the 1600s, people were experimenting with lenses. People had made magnifying lenses, probably going back as far as the Greeks. However, putting one lens in front of another and looking through them both was a fairly new thing in the 1600s. And it rapidly became known throughout Europe and was considered to be...
Was it designed in Europe?
It was possibly discovered by children playing with lenses in a spectacle maker's shop and saying to the optician, look what happens when we put these two together like that, how you can see the weather vane on the distant steeple. And so the idea came up, oh, we could use this to see when our ships are coming in so that we can make a killing on the stock market before anybody else sees that our ships are coming. Or we can look and see if the enemy ships are coming, and we can estimate what we should do in order to triumph in battle. But then Galileo got a hold of it, and he pointed it at the sky and looked up and saw things that no one had ever seen before. He saw that the Milky Way was composed of great numbers of faint stars. He saw that Jupiter had 4 moons going around it, which no one had ever seen. He saw that Venus changed its shape over the course of the months, the same as the moon changes its phases. He saw that the moon had mountains, and he had a way to estimate the height of them using geometry. So many discoveries were made in a very short amount of time that supported an idea about the universe that was completely revolutionary for the people of his time. He was such a fright to the powers that they placed him under house arrest for the rest of his years because they felt so threatened by the ideas that he was espousing. These ideas began to emerge in the late 1400s with a man named Copernicus. Like many people of his time, like Galileo and many, many others, he felt that astrology, the fortune-telling business by which many of these people made their living, would be improved by more accurate predictions of where and when the stars appeared. And particularly, they were bothered by when and where the planets would appear. And Copernicus took measurements of the angles that the planets would take. And from those angles, he was able to determine a scale model of the solar system using trigonometry.
Oh, good.
He measured with the unit of the distance between Earth and the Sun as 1. We now call that the astronomical unit. We use it for measuring distances within planetary systems. And compared to this 1, this unit of distance between Earth and the Sun. What is Venus's angle? And he found it to be about 0.72. What is Mars? Mars turns out to be about 1.5 of these astronomical units. And he laid them out planet by planet, this is before the telescope, and determined a scale model of the solar system with the sun he placed in the center, and the day and night he explained as the turning of Earth on its axis. These were ideas that were startling in their time and very slow to gain acceptance. But there was much debate in those days about what was the true structure of the solar system, dating back to Aristotle and Ptolemy in the Greek times. They believed that the universe was small, that Earth was the center, and that everything that moved in the sky was mounted on crystal spheres, the celestial spheres, and that they moved. And it's hard for me to tell in our present day whether they used this as a mathematical hypothesis because they could predict things based on this model, even though it was wrong. It would still tell them when and where approximately to expect to find things. But in the 1500s, Tycho Brahe, a Danish aristocrat, saw one of these exploding stars of which I've spoken. And this change in the sky ran counter to the idea that the heavens were unchanging. And he began to question the measurements of the ancients and take more accurate measurements than had ever been made before. And he had great wealth with which to do that. And because they had no electronics in those days, he hired a young man named Johannes Kepler to be his computer, a human computer. And Kepler took these extremely accurate observations of where things were in relation to each other in the sky, and through years of calculation realized that the motions of these objects through the sky were not circles but ellipses, that their speed was not constant, but that they sped up when they were closer to the sun and slowed down when they were further.
Now, how was that?
Eventually,
what caused that cycle of activity?
Eventually, Newton came along and understood that the relationships that Kepler saw between the astronomical unit and the time that it takes for this planet to go around, and the shorter amount of space and the shorter amount of time it takes for the inner planets to go around, like Venus and Mercury, and the longer times that it takes for the outer planets to go around, like 30 years for Saturn to make one orbit of the sun at its distance, that all of these related to the sun and sung, in a way, the harmony of the sun's mass to control the distances and the times of all the objects in our solar system.
What's the progression of the telescope?
We go from a toy that was sold at carnivals to an instrument that was considered a top secret weapon of war, in the same way that we look at radar to detect the approach of our enemies today, to Newton, who decided that instead of looking through glass lenses, he would polish a curved mirror like the inside of a spoon and focus the rays of light from the stars onto that mirror and then capture them in another mirror like a periscope and look at that with a magnifying glass. And then expanding on that idea, we're now able to take such a structure and put it into space so that we are no longer limited by the cloudy night, or that the telescope can't be used in the daytime when the stars.
So we're talking about the
show.
Hubble.
The Hubble.
The Hubble.
Named
What's the largest leveled telescope? Where's it located?
I believe in Chile.
Where?
In Chile.
Chile.
Yeah.
Chile.
High up in the Andes Mountains in the Atacama
okay.
Desert.
All right.
And we have a succession of increasingly large telescopes being constructed around the world, mostly in the highest places that are also dry. High, dry, mountainous areas like the top of Mauna Loa in Hawaii, like the Canary Islands, like the Andes Mountains in Chile. Many, many telescopes. Very, very large telescopes.
Now, do they talk to one another?
They not only talk to each other, but by combining the images from many telescopes in many places, both on Earth and now in space, we are able to consolidate all of their images together as if these were telescopes of even greater size than could ever physically be constructed.
Where's the largest Hubble, the largest telescope in this country? Put its foot down.
Well, you'd have to remember that Hawaii is part of this country.
Okay.
So we'd be
All
talking
right.
about,
you did say Hawaii.
we would say Mauna Loa.
Okay. All right. Let's have a little discussion about astrology. Let's talk about how did astrology begin, and what's this? How does it? Hang on. How does it fulfill its purpose?
Well, what purpose are you seeing in it?
I don't.
Well, I don't either, except in the historic sense,
Okay.
that the feeling that you could tell people's fortunes better if you had more accurate measurements of the sky could motivate the people who made their living by fortune telling for the wealthy. You could be motivated to develop a science which more accurately measured the motions and came to understand how these objects led to the formation of our place and of ourselves, because we are composed of elements that were created, if you will, in the stars themselves, in these places of the greatest density and the strongest forces in the universe that are able to transform the atoms into the different substances.
So astrology does what?
Astrology.
It talks to us about astronomy.
Are you talking about the horoscope in the newspaper? Because I don't think the people who write those.
No, I'm talking about astrology as such. That bit of quasi-science, I can understand.
Well, I think the quasi-science became separated from the stars themselves, because the stars themselves change their positions over very large spans of time. But human society has existed for long enough now that those motions have taken place. And so the patterns that were spoken of in this culture at this particular time have shifted measurably in the thousands of years, and the astrologers of today are writing columns in the newspapers that don't involve them actually looking at the stars or thinking very much about the reality of the universe. They're talking about how do you make a generalization that someone could use as advice to organize their life if they didn't have their own ideas of how their life should go.
Well,
You know, for people who are so lost,
no.
then perhaps reading in the newspaper what you should do this morning is helpful. But for those of us who know what we're about, we don't have any need of that anymore. But that was from a period of superstition in our world. And, you know, we may fall back to an era of superstition again if education fails us.
You think astrology is superstitious related?
Yes.
You do? Why is that?
Well, it's not based on
It has some
reality.
limited basis in science.
Excuse me?
It's more in religion than in science.
Okay, so, you know, what can you say? You know, that, I forget who says it, but, you know, science tells us about the age of rocks, not the rock of ages. You know, religion has one role to play and science has another. There's lots of different ways of accessing wisdom in human civilization. Religion is one of them, science is another, but they're not the same thing. But they came from the same roots. There was a time when these things weren't as separate as they are now, when the people who had knowledge were also the people who had power, were also the people who controlled religious beliefs and rituals. And that has changed over time.
I understand that recently there was another star discovered. Wasn't there some loud noises in the news about a star that was discovered recently?
I think a lot of the news that we read about astronomy these days concerns a development that only began to be possible in the 1990s. And this was when the analysis of the light from stars went from looking at these variations in brightness that are true of stars that have a certain instability that causes them to expand and contract, like these Cepheid variables that Henrietta Swan Leavitt first wrote about in the early 20th century, to beginning to look at how there can be variations in the brightness of stars caused by one star going around another star, and you can measure the masses of these different kinds of stars by how far apart they orbit each other and by how long it takes them to go around, using the same mathematical formula that Kepler discovered around the time that the Pilgrims came to Plymouth Rock. And when Newton, a few years later than that, determined that this told us the mass of objects related to the mass of the sun, it became possible to compare the sizes of different stars based on stars that went around one another. And Herschel in the 18th century was the first person to make these measurements to compare other stars to our star, the sun. And then down in the 1990s, it became possible to look at curves of light, periods of a star's dimming, and recognize that this was being caused by a planet going around that distant star and coming between us and the light of that star, so that that star would briefly be dimmed as the planet went between us and that star. And so we began to talk about exoplanets, planets going around other stars, planets in other systems, and this had never been witnessed until the 1990s. And missions were established to investigate these, notably a space telescope named for Kepler, and thousands of such planets were detected orbiting distant stars. And the search has become particularly keen to see if we can find such a planet that is in the right position to its star, that it could have liquid water.
Now, is it the problem that we can't see all the stars so we can identify them, or are new stars being made from colliding stars?
New stars are constantly forming. There's a notable constellation, Orion, that we see in the wintertime. And just below the three stars of Orion's belt, we can see a cloud of dust and gas. And when the Hubble Space Telescope focuses in on this nebula, this cloud of dust and gas, it can actually see the disks that are forming around these bright areas that are stars coming into birth. And there are similar objects found in the parts of the sky that are named for other constellations. So in the constellation Taurus, for example. And so we now use these connect the dot pictures, the 88 constellations, if you will, to say this part of the sky different from that part of the sky, and to identify, the Andromeda galaxy is located in the constellation we call Andromeda. And so the traditions of astronomy and astrology are used now as the mappings, in the same way that, we name Massachusetts after the people that lived here hundreds of years ago. And we look and we see the signs of these planets, and people want to know, are the conditions on that planet such that there could be life? Are there people there who could be looking back at us? And that would depend on whether that planet was not too close to its star, that all its water would be boiled away, not too far from its star, that all its water would be frozen like ice, but just right, like in the Goldilocks story. And if that's the case, what evidence can we find? What would we be looking for? We'd be looking for signs of organic compounds like methane and carbon dioxide, things that would be required for photosynthesis. Oxygen would be a sign that carbon dioxide was being photosynthesized into another substance.
So what are the largest stars in the universe?
Well, one of the largest is located not so far from us. It's the brightest star we can see in the wintertime, Sirius, the dog star.
The what star?
The dog star, Sirius. If you go back to the ancient stories of the people who hunted the wild cattle before cattle were domesticated, you see a mighty hunter, Orion, who is fighting against Taurus, a bull. And Orion is assisted by his dogs, Procyon, the little dog, and Canis Major, the large dog, right? So we have these stories in the sky that go back tens of thousands of years. And we have modern abilities with telescopes to look at these constellations and the stars within them and figure out what their structure is and their size and what they're made of. And so, if we look at Sagittarius, which looks a bit like a teapot in the summer sky, right between the spout and the lid, we see that is a source of tremendous radio energy radiating out from the center of the Milky Way galaxy. And we've determined that is a supermassive black hole, more massive than hundreds and hundreds of suns, and that our entire galaxy orbits around that central object.
Do black holes have names?
That one is called Sagittarius A.
Sagittarius A.
Yeah.
Joel, I'm telling you, I've got it all up there. I mean, it's it's racked and someday you'll ask me to regurgitate, spew it out to you, give it all back. Right?
I'll ask you to give me the link so that I can share it with my students who are very excited to hear that I was going to be doing this with you tonight.
Very interesting. Very interesting. I like this subject. Yeah, and of course I still had some ideas about astrology. I guess I'll have to find them some other way. I was interested in how they get these names, Taurus and Sagittarius. What sort of some of this sort?
Well, most of the names that we use.
There are 12 names.
The zodiac.
Yeah, zodiac. Yeah.
So these are the constellations that are in the plane of our solar system. The plane of
Is it only
objects
12?
orbit.
It has to be more than 12. But
Well, the Babylonians had a system of mathematics that was based on multiples of 12.
oh, okay.
And so,
So it is 12.
they tried to figure the number of times that the moon goes through its phases in relationship to the seasons of the year. And it didn't quite work out, but it was very close to 360. So we now break up our circle into 360 degrees, and we have 365.25 days in a year because it turned out that it was a little bit more than 360.
Yeah.
But back then it was a little harder for them to figure these things out,
Yeah.
But calendars and timing, and the repeating cycles of the year, which people took great interest in because it determined their livelihood, when food would come, when the winds would blow in the right direction so that they could travel where they needed to go, and all of these matters.
Very good.
Well, thank you so much.
I want to thank you.
Thank you so much for having me.
Thank you for joining me. And I'm sure that, I'm sure that the people who listen in on the program will enjoy this and derive at least a little bit of education from it. And I want to thank you for listening in. You have been good to stay with us and share our views and ideas. And I hope that you hang around because we have more good stuff coming. Thank you, and I am Richard S. McGee, and good night.